Okay. So let's start. Thanks for the introduction from Professor Lin Qisong. Hello everyone. My name is Qiaosheng Zhang from Shanghai AI Lab. So today I will talk about something about using information theoretic method for reinforcement learning. Yeah, this is the outline of my talk. So first, I will give some motivation of studying reinforcement learning. And here I classify reinforcement learning into single agent RL and multi-agent RL. So for single agent RL, I will first introduce the mathematical formulation, which is the Markov decision process, MDP. And then we will present an algorithm called information directed sampling algorithm, which leverage some information theory concepts such as mutual information and lossy compression. And we also show that this algorithm achieve theoretical guarantees of the performance which almost match an information theoretic lower bound. And for multi-agent RL, we first introduced the mathematical formulation, which is Markov game. And we also present a multi-agent version of the information-directed sampling algorithm. So people have been talking about machine learning for many years, and machine learning is mostly about predicting patterns. And the typical applications of machine learning include image classification, object detection, and machine translation. And reinforcement learning is kind of different. Although people view reinforcement learning as a subfield of machine learning, but it is mostly about making decisions. So typically in reinforcement learning setting, there's an agent who interact with an unknown environment and to do some action and receive some reward. And through this reward, the agent can learn the environment better and better. And finally, the objective of the agent is to make some good decisions. So reinforcement learning has also some applications such as robotics, game playing, and autonomous driving. So I think most of you have remembered that several years ago, DeepMind has developed AI software called AlphaGo, which is which an expert in the game of Go, and it also beat the world champion several years ago. And also in the recent 2 years, people are talking about large language model, ChatGPT, and of course, in addition to ChatGPT, there are some open source large language models such as Llama 3 and Intern LM, which is a language model developed by Shanghai AI Lab. So during the training process of this large language model, there are typically 3 steps. The first steps are pre-training, and the second step is supervised fine-tuning. For the last step, it is called reinforcement learning from human feedback. So RLHF in short. So the second step is also very important, which make sure that the output of large language model is aligned with human preference and also make sure the safety and the robustness. So the previous example demonstrates that reinforcement learning is really a promising field that has lots of real-world applications. And perhaps more importantly, reinforcement learning has relatively well-defined mathematical framework that allow our information theories to make some contributions. So although reinforcement learning has achieved tremendous success, but there is a very important challenge, which is called the data efficiency. This is because collecting data in real world is very time-consuming and expensive. So for example, in this AlphaGo example, we know that it is trained on more than 10 to the power of 7 episodes of games, and it took more than 1 month. So it really means that training is very time-consuming, and we wish to use as few data as possible to learn a good policy. So the main question we want to ask is that, can we establish a theoretical foundation for reinforcement learning, particularly focusing on data efficiency? So as information theorists, we want to answer this question from two sides. The first is, can we establish information theoretic lower bound on data efficiency? The second one is, can we design algorithms that approach this information theoretic lower bound? So first, I will talk about single agent RL. So in this setting, there is only one agent who interact with an unknown environment, and the goal of the agent is to maximize the reward. So I use a very a classical figure in reinforcement learning. So the agent is in a state S, and he takes some action A, interact with the environment, and the agent can receive some reward R, and then the state S will transit to next state S prime. So this is the typical loop in reinforcement learning. And you can imagine through this example of maze. So in here, this maze is just the environment, and the agent is this little mouse. And in this example, the state is just the location in the maze. You can represent the state by its x-axis and y-axis. And the action is you can either move up or down or left or right. And in this case, the reward is just the cheese hidden in the maze. So the agent the mouse want to collect as many cheese as possible. So we want to consider a so-called finite horizon setting, which means that the whole game terminates after capital H steps. So this is more interesting because if we consider infinite horizon setting, then the agent, the little mouse, can use infinite amount of time to learn every details in this environment, so that he can learn it very well and choose a best policy. But this is not very interesting. So a more interesting setting is that this game only will terminate after a finite step. Here we use H to denote the number of steps. And the agent should learn this environment and make good decisions constrained within this finite horizon. So here I will introduce the interaction protocol between the agent and the environment in this Markov decision process. So initially, the agent is in the state S1, and for each step, H from 1 to all the way to capital H, the agent observes the state SH, and then takes observe the state SH, where SH belongs to the so-called state space with capital S. And the agent will take action AH, which belongs to action space capital A. So the agent will observe a reward RH, which follows from a distribution capital RH. And here, this distribution capital RH also depends on SH and AH, depends on the current state and the current action. And then the environment will transit to the next state SH plus 1, which follows from a distribution PH, which is a probability distribution over the state space and conditioned on the SH and AH. So here, this PH is a state transition probability, which looks like the channel transition probability in information theory. So I'm always talking about the environment. So here, the environment in Markov decision process really means two things. One is the transition probability distribution PH, and the other is the reward distribution RH. And of course, we need to consider PH for all H and SA, and the reward RH for all H and SA. So the agent want to use some policy to interact with the environment. So the policy is defined by this pi. Actually, this pi contains capital H sub-policy, denoted by this pi H. So each pi H is a mapping from the state space S to the action space A. Here we use this capital delta A means the probability simplex over the action space A, which means that the policy pi H is actually a stochastic policy, not a deterministic policy. So if the agent adopts the policy pi, then we can go back to look at this this interaction protocol. Then this AH, the action that the agent select follows from this pi H. So the goal of this in this Markov decision process is to find the optimal policy denoted by pi star that maximize the value function v pi. So here, this v pi is nothing but the expected cumulative reward from the first step h equals 1 to the final step capital H. And here, this expectation is averaged over S1, A1, R1, S2, A1, A2, R2, all the way to S capital H, AH, RH. This is what we call trajectory. And here, this AA, we have a superscript in this expectation notation. So this superscript pi means that the agent choose the action AH follows from this this policy pi H. So if the environment, if the transition and the reward function were known to the agent, then it is very easy to compute this optimal policy. And this can be done by some classical method, such as dynamic programming. However, in reality, in the reinforcement learning setting, we do not know the environment at the very beginning. So the agent should learn the environment through many episodes. So this comes to the episodic setting, where learning happens. So in the episodic setting, we have many episodes, T from 1 to capital T. And the interaction protocol for each episode is just the same as what we introduced before. Here, I just put a superscript T to each of the notations to indicate the dependency of to the number of episode T. So intuitively, when the agent interacts with the environment for one episode, he will receive some feedback and he will learn more and more about the information. Learn more information about the environment. So intuitively, as the number of episodes increase, the agent can learn better and better about the environment, so he can further do better and better decisions and to output some better policy. So how do we measure the goodness, or how do we measure the performance of an algorithm through these capital T episodes? So this can be measured. The performance of an algorithm can be measured by this PAC guarantee, which means how many episodes are needed for algorithm to find a policy pi hat, such that the value of pi hat is absolutely close to the value of the best policy. Here, this max pi v pi is the value of the best policy. So here, PAC means probably approximately correct. So probably means that we want that after a number of episodes, this proposition holds with high probability. And approximately means that finally the learned policy pi hat is absolute. The value is absolutely close to the value of the best policy. And PAC guarantee is one criteria to measure the performance of algorithms. And we also introduce another criteria to measure the performance of an algorithm, which is the regret. So here the regret is over capital T episode. So it's over the full learning process. And it is defined by, for each episode, small t, we calculate the suboptimality of this pi t. The value of pi t, actually it is the value of the best policy minus the value of the policy pi t that we use. And then we sum over all the episodes. So we hope that the regret over this capital T episode scale sublinear in this T. And ideally, we hope that it scale as order square root of T. So this is the second criteria for to measure the performance of algorithms. And in fact, the second criteria, this regret is even stronger than the first one, the PAC guarantee. So in the remaining of the talk, I will focus on analyzing the regret of algorithms. So I think you may have heard of this multi-arm bandit problem. It is actually a special case of reinforcement learning with a single state and one step. So in the multi-arm bandit setting, it's just if I go to a casino and I find a bandit machine with multiple arms, and initially I don't know which arm is good. So I just pull each arm for several times and try to figure out which arm is good. And so eventually I want to pull the best arm to get as many rewards as possible. So in this multi-arm bandit setting, we don't have the concept of state and we don't have the concept of step. So it is much simpler than reinforcement learning. It is only that for each episode, I take an action and I receive a reward, and then I go to next episode. So this is just a special case of reinforcement learning. So in both reinforcement learning and the multi-bandit problem, there's a big issue called, the most important issue is that we can only see the response for actions that has been taken. So, then for the next round, I have two options. The first option is that I do exploitation. That is, I take action that we already think it is a good action. And the second option is that I do exploration. That is, we take new actions to gain more information about the environment. This will be helpful for my future decision. So in reinforcement learning, it is a common sense that good algorithm should balance exploitation and exploration. And here we notice that for exploration, we need to gain more information, but for our information series, we want to ask a question, so whether we can measure this information through some information theoretic quantity or some information measure. So the answer is yes. So this can be achieved by the so-called information-directed sampling algorithm. So since we want to measure the information of the environment, so we have to assume that the environment is a random variable, so that it contains some information. So we use this calligraphic E to denote the information, to denote the environment, which is a random variable, and we assume that the prior distribution is known. So in learning literature, this is called the Bayesian setting. And in order to do exploration, we want to maximize the information learned by a policy pi. So how do we measure the information? So we use the mutual information term, which is I, E, and TH. So here the mutual information is about environment E and TH. Here TH is a trajectory which contains S1, A1, R1 all the way to SH, RH, which is a whole trajectory that the agent can observe at the end of the episode. So here I put a subscript pi here. It means that the action A follows from the policy pi. So this is how we measure how many information can we learn through the interaction with the environment in this episode. So in this way, we can use the information measure to measure the information that can be learned about the environment. And also we can not only do exploration, but we should also do exploitation. So to do exploitation, we need to minimize the expected regret incurred by the policy pi. So here the expected regret is defined similarly as before, but just we take a expectation over the randomness of the environment. And next I will introduce an important concept called information ratio, which gamma pi, which is a ratio between the squared expected regret and the mutual information. So we eventually want to minimize this information ratio so that we automatically minimize the expected regret and we maximize the mutual information. That is, we both encourage exploration and exploitation. So given the concept of this, given the concept of this information ratio, then the description of the algorithm is quite standard. So for each episode, the agent just compute a posterior distribution of the environment based on the prior distribution and the past trajectory that he observes. And then the agent chooses the policy so-called pi IDS T at episode T, which is a minimizer of the information ratio. That is, I choose a policy pi that best that balance the squared expected regret and the mutual information learned about the environment. So actually, this kind of information directed sampling algorithm has quite good performance guarantee. So we can show that the expected regret of the algorithm scale as this square root of this so many things. But the important thing is that it scale as square root of t. So this is which we desired. And if we look at the information theoretical lower bound and the regret bound of IDS, we compare these two bounds, we notice that our algorithm is optimal with respect to the number of episode t. Of course, you may notice that there's some logarithm log term, but usually in reinforcement learning, we do not care about the log term. And second, our regret bound is not optimal with respect to other parameters such as S and A and H. So it means that we have there's some space to improve. And the final remark is that our algorithm can also be implemented in a computationally efficient manner. So I just use one line to sketch out the proof because we really don't have time to go to the details. So we use some techniques like Bayesian model averaging and Pinsker inequality and some standard information inequalities to handle the mutual information, KR divergence, or TV total virtual distance, something like this. So just now I have said that there's still some room to improve the IDS algorithm. And here we also give improvement of this IDS algorithm, which is inspired by lossy compression. So the key idea is that in the environment, we do not really need to learn every detail of the environment because there are some redundant information in this environment. So we want to compress the environment according to some lossy compression techniques. So the first step is that we assume, firstly, we assume the environment E is supported on a space capital theta, and then we will partition this capital theta into disjoint subspace theta k epsilon, such that for any pair of environment E and E prime, which belongs to the same partition, then the value of the of any policy on these two environment E and E prime should be very close. So roughly speaking, this is a distortion measure that measures the similarity and difference between two environments. And we hope that we partition the entire space theta into many disjoint subspace such that each subspace only contains environments that are close to each other under this distortion measure. And we also need to figure out how many subspace we need to do the partition and to do the lossy compression. And in fact, we can also give an upper bound on this, the number of K, the number of partitions here. We use some technique like covering number. And then for each subspace, we define its subspace center as this EK, which is some conditional expectation term. And then finally, we need to construct the compressed environment E tutor, which is also a random variable and which is correlated with the environment E. And such that this E tutor equals to EK if and only if the original environment E belongs to the subspace E epsilon K. So once we have we define the compressed environment E tutor, then we can describe our algorithm. So which is the so-called compressed IDS. So for each episode, we first calculate the posterior distribution of the environment E, and then we construct the compressed environment E tutor such that according to the construction rules that I described before. So finally, we choose the agent choose a policy high IDST for episode T as the minimizer of the information ratio. Here, this information ratio is similar to the previous one, except that we change the mutual information term from E to E tutor to the compressed environment. And also for this compressed IDS algorithm, we also have theoretical guarantee on the Bayesian regret. And it turns out that this regret is better than the previous regret, and it reduced the factor of S. So this is how we design the IDS algorithm and the compressed IDS algorithms for single agent reinforcement learning. And next, I will introduce the multi-agent version of reinforcement learning. So in many applications, it involves more than one player. For example, if we consider the AlphaGo example, so there are two players, and the action of the other player also affect the reward that I can receive, and also affects the transitions of the game. So in this case, the two players are in a competitive nature, and we model this two-player reinforcement learning by the two-player zero-sum Markov game. And we refer to the two players as max player and min player. So the interaction protocol is very similar to single-agent reinforcement learning, but here I highlight the difference in this boldface letter. So for each step, both player will observe the state SH, and both player will take action simultaneously. So the action is denoted by AH and BH. And then the max player get reward RH, and the min player get reward minus RH. So here this reward is reward for the max player, but it is really the loss for the min player. And then the state will transit to the next state according to some transition probability distribution. And notice that here the reward depends on the state and the action of both players. And also the transition depends on state and the action AH and BH for both players. So maybe we call the max player's policy as pi h, and we call the min player's policy as mu h. So here I use a figure to illustrate this Markov game. So really it is a Markov structure and sequential game. So a very important concept in this Markov game is called the value. So for each pair of policy pi and mu, we can define the value v pi mu as expected cumulative reward and also expected cumulative loss for the min player. So this expectation is also averaged over S1, A1, B1, R1 from the first step all the way to the last step. So here the AH and BH, this action are taken following from the policy pi h and mu h. So in the Markov game, how do we define a good policy? So if the opponent's policy mu were known, so suppose we are the max player. So if the min player's policy mu were known, then the max player can choose the best response, this BR mu, which is a maximizer of the value v pi mu. However, in reality, the min player's policy is not known. So in this case, the best way to define a good policy is a Nash equilibrium policy. So it has been shown that in Markov game, there exists a Nash equilibrium policy pi star and mu star such that no player has incentive to change if the other player do not change. And also this Nash equilibrium policy pi star and mu star have a very good property is that let's say this pi star is arcmax pi v pi br pi. So it means that if I'm the max player, I use policy pi, and my opponent can always use the best response. Then what should I do? I should choose this pi star because this pi star is optimal when the opponent can always choose the best response. So we can also say this pi star is the best response to the best response. And also for the min player, it is the same. This mu star is also the best response to the best response. So for learning in this two-player zero-sum Markov game, we also consider this episodic setting where learning can happen. So for each episode, T from 1 to capital T, so both players follow the interaction protocol that I introduced before. And we want to measure the regret of one player, or we can measure the regret of both players, but for simplicity, we can first define the regret for the max player. So the regret for the max player can also be defined similarly as the single agent version. So ideally, we hope this regret over T episode scale as order square root of T. So here the message is that we can also design an information theoretical sampling algorithm for multi-agent reinforcement learning for this setting. here, if we want the max player can learn some good policy, then we follow this algorithm. But I think due to the time constraint, I will not introduce the algorithm in detail. But the message here is that we can also use information directed sampling to learn a good policy for both max player and mean player, and we can also derive some regret bound for this information directed sampling algorithms, and this regret bound is also optimal with respect to the number of episodes T. And also, there are some remark of the algorithm, and I will not go into the details due to the time constraint. So finally, I will conclude my talk in these slides. So first, IDS, information direct sampling, is an information theoretical inspired algorithm for reinforcement learning that has theoretical guarantee. And it showcases how information theory can help reinforcement learning or in general AI. And also, as I introduced, so when designing this IDS algorithm, we use the concept of compression. So the compression of the environment really help us to improve the performance of IDS algorithms. However, it is still not optimal. Maybe our compression method is not optimal at the current state. So for future work, it is very interesting to look for new compression method that can further help IDS. And I think this is a good opportunity for information theorists because nobody knows how to do the compression better than information theorists. And finally, there are some open questions. So can this IDS principle, this information theory inspired principle, apply to some other more complicated or more complicated scenarios, such as some general functional approximation, which can handle the large state and action space, and also for reinforcement learning with human feedback for large language model, can we design an information theory-driven method that help the training process of large language model? So this is all my talk. So thank you.
All right. So any questions to our speaker? So from our audience.
About the multi-engine multiplayer reinforcement learning. So just assume all the players, they will observe the state from the same state space, right?
Yes.
So how about the heterogeneous environment? You know, maybe the engine they are located in different environments. They will see different state environments. So have you ever thought about that? Heterogeneous environment.
Okay, that's a very good question. But for the current, I know there's a lot of variants of reinforcement learning and multi-reinforcement learning, but at current stage, we just consider the most traditional setting that both players are sitting in the same state space. And I think, in the future work, it is also interesting to see whether this principle can generalize to the setting that you mentioned. I think this is a very interesting observation. Thank you.
Yes, for your algorithm, actually, you need to package the information.
Yes.
But we don't know the environment.
Yes, we don't know the environment, but actually we have a prior distribution that this is known. And
so I guess my question is how accurate that information is in terms of exploring the environment.
Yes, this is a good question, but I think in this algorithm design, we do not because actually here we also hidden some constant here because the important thing is that we use the two terms, the numerator to do exploitation and the denominator to do exploration, and actually we can also add some constant or something else to do some finer analysis of the algorithm. But at the current stage, what we can show is that even we don't care about this constant, this scheme still works very well. And for the final result, for the theoretical result, we can show that we can have some constant, but actually this constant is not the most important thing. So I assume if we can do better analysis, then we can get better constant, but that may be of interest to the future work.
Yeah, I agree. It's very interesting direction.
Thank you.
Most unknown.
Following Professor So's question, so as the package getting longer and longer, how to calculate the major variation?
Yeah.
I think the major variation is related to the package, right?
Yeah. The mission is related to the whole trajectory. Yeah. So how
as the getting longer and longer, how to?
Yes. So actually, this is a very good question. So I mentioned that our algorithm is a computationally efficient algorithm, but I did not introduce how to calculate this mutual equation. So the reason is that actually we can convert the whole information ratio term to some other term, so that we don't really need to calculate the mutual equation. So we have some approximate method that can approximate both the numerator and denominator, and we can show that the approximation is accurate up to some distortion.
Okay, thank you. So another question is, can you compare the new metric and the new metric? What is the regulation result compared to the other?
Okay. Yeah, that is also
improved or something.
Yeah, that is also a very, very good question. So up to now, we only perform theoretical analysis, have not go to the experiment part, because for the IR setting, it is quite complicated, and we need to compare with some deep learning based method. So that may be the comparison should be very interesting. Yeah, but we have not performed such comparison. Thank you.
Comparable or with the?
I think from a theory perspective, it is comparable, but we need to in real application, this is still unknown. Yeah.
So for each episode, do you need to search across all the policy space to find the policy maximize?
Yes. Yeah, this is very good. Yes. So in the current algorithm description, we need to search over the whole policy space, but in our approximation of our algorithm, we avoid this search over the space, so that we can make our algorithm more computationally efficient. So I think this question is similar to Professor Ma's question, and it is a very sharp observation, and which I did not introduce during my talk. But in our paper, we do show that we can approximate the algorithm using some other method, so that we avoid such computationally inefficient approach.
So environment here refers to like the problem formulation, like a transition model, reverse function, or is like it just states?
The environment means the transition probability distribution and the reward distribution. Yeah, so the state space and action space are known to us.
Okay, so any more questions?